Welcome students. In today's class we will start off with a review of the previous topic that we studied in lecture 3. Also in this lecture we will understand about integrating quantities using integration by parts. So foremost, to solve this question we make the observation that this is of the form linear over root of quadratic type. So when we have this type, we will rewrite the numerator as lambda times differentiation of the quantity inside the square root. That's 8 times x positive 4 positive mu. Now we will distribute this quantity. This is going to be 8 times lambda of x positive lambda 4 or 4 times lambda positive mu. On the left hand side we got x positive 3. So if I were to equate the coefficients of x, I would get 8 times lambda is equal to 1, therefore lambda is equal to 1 over 8. This is one part. The other one, if I were to equate the constant term, I would have 4 times lambda positive mu is equal to 3. Lambda is 1 over 8, so this would give me 1 over 2 positive mu is equal to 3, and mu is equal to 3 negative 1 over 2, which is 6 negative 1 over 2, which is 5 over 2. This is my mu. So having obtained lambda and mu, x positive 3 is now equal to 5. I should have 1 over 8. So 1 over 8 of 8 times x positive 4 positive 5 over 2. So this is what I have got, and we are going to use this to solve this question. So hence we can rewrite integral x positive 3 over root of 4 times x squared positive 4x negative 3 times dx to be as integral. In place of the numerator I will substitute the quantity on the right hand side. It's going to be 1 over 8 of 8 times x positive 4 positive 5 over 2 over square root of 4 times x squared positive 4x negative 3, and you got the dx operator there. So we will be rewriting the integral into two quantities. So this is going to be 1 over 8 integral 8x positive 4 over square root of 4 times x squared positive 4x negative 3 with the dx there, positive 5 over 2 integral dx over root of 4 times x squared positive 4x negative 3. So I've got I1 and I2. So I will start off by considering I1. So let us consider I1, which is 1 over 8 integral 8x positive 4 over root of 4 times x squared positive 4x negative 3 with the dx there. I will start with the substitution of 4x squared positive 4x negative 3 to be equal to t squared. Differentiating both sides we get 8x positive 4 times dx is equal to 2t dt. So this can be rewritten as 1 over 8 integral. In the place of the numerator I will substitute 2 times t dt over root of, in place of 4x squared positive 4x negative 3 I will substitute t squared. 2 divides 8 4 times, so it's 1 over 4 integral t times dt over root of t squared is t. I can cancel the t's here, give me 1 over 4 integral dt. Integration of dt would give me t, and that has to be divided by 4, but my t squared is this, and so my t would be root of 4x squared positive 4x negative 3 divided by 4 positive arbitrary constant c. Now let me consider I2. The I2 is 5 over 2 integral dx over root of 4 times x squared positive 4x negative 3. I want to take the 4 out from the denominator, so that would give me a 2 outside with the quantities x squared positive x negative 3 over 4. Right? When you take 4 out, this is what you will end up with. 2 multiplied with 2 will give you 4, so it's 5 over 4 integral. Now I want to write x squared positive x negative 3 over 4 as a perfect square. So that is achieved by adding 1 over 2 squared and subtracting 1 over 2 squared, followed by the quantity 3 over 4 with a negative sign. So this entire quantity is rewritten as x positive 1 over 2 raised to the power of 2. If you simplify negative 1 over 4 with negative 3 over 4, you would get a negative 1 there. So I can use this instead of this. So that's going to be integral dx over root of x positive 1 over 2 raised to the power of 2 negative 1. Instead of writing 1, I would write it as 1 squared. Now we know a formula. What do we know? We know that integral dx over root of x squared negative a squared is equal to ln of x positive root of x squared negative a squared positive arbitrary constant c. So I would be using this formula over here. So that's going to be 5 over 4, and you will start with ln of x positive 1 over 2 positive root of the quantity which is present in place of x, that's x positive 1 over 2 raised to the power of 2 followed by a negative 1. Now I can make the following simplification, or if you choose not to make the simplification, you can just retain this as it is. So the final solution, therefore I1 positive I2. So what exactly we got in place of I1? Let me show you that. So write that down. So this is equal to 1 over 4 root of 4 times x squared positive 4x negative 3 followed by a positive 5 over 4, and then you got ln of x positive 1 over 2 positive root of this quantity, that's x positive 1 over 2 raised to the power of 2 negative 1 positive arbitrary constant c. So this is a beautiful question which we have just completed, and it is a good place for us to draw the red line. So we move on to the next question, students. Students, we will start off with integration by parts. This is very important concept in indefinite integrals. So the formula, I would like to give you the formula. The formula is uv negative integral v du, and on the left hand side we got integral u dv. So this is the formula which you will have to know. Of course there is a theory part which is involved in creating this formula, but we will restrict our understanding, or I would say the focus for this class is the application part of the formula. And having mentioned that, we will assign the values of u based on Liet. Now L stands for logarithmic functions, I stands for inverse functions, A stands for algebraic functions, T stands for trigonometric functions, and E stands for exponential functions. So the best way to understand the concept is by doing more questions. So foremost, this is the way by which we assign terms to u. That is the most important thing, and everything else that is left will be handled with the dv term, right? So I'm talking about the left hand side. Please remember, we use this concept known as liet to assign the term to u, and everything else that is left after assigning the term to u, we will take it for dv. So having mentioned that, let us start off with a basic question. So this is a very simple question. Integral of x times cos x dx. We are assigning values for u. So clearly from this we can see that the algebraic quantity is x. So we take it as u, and anything else that is left after assigning the quantity for u is taken to be as dv. So dv is cos x dx. So let us write the formula. The formula is u dv is equal to uv negative integral v du. So according to the formula, this is going to be integral. In place of u I got x, in place of dv I've got cos x dx. So that is fine. We got the question back. Now to get the values for du and for v, we will have to differentiate this. Upon differentiation of u, we would get du. Differentiating x would give us dx. In this case we will have to integrate. So integral of dv will give us v. Integral of cos x would give us sin x. We don't have to place the arbitrary constant here. So now substituting the values after we have completed this, this is going to be u is x, my v is sin x, followed by integral of sin x, my du is dx. So this is equal to x times sin x. If I were to integrate sin x, I would get a negative cos x. Now this is rewritten as x times sin x positive cos x, positive arbitrary constant c. So this is a good place for us to draw the red line. So this is the solution for the question that we were given. So we will move on to the next question. So let us do this question. We are asked to integrate x times e raised to the power of x times dx. So clearly you can see we have an algebraic quantity x there. So I'm going to state let u be equal to x and dv be equal to e raised to the power of x times dx. I differentiate this, I get du is equal to dx. I integrate this, I get v is equal to e raised to the power of x. So the formula, integral u dv is equal to uv negative integral v du is now rewritten as, with the quantities that we have, u is x, my v is e raised to the power of x, followed by a negative sign and an integral of v du. So my v is e raised to the power of x, my du is dx. This is nothing but x times e raised to the power of x negative. If I were to integrate this, would give me e raised to the power of x. I can just take e raised to the power of x out and write it as x negative 1 with the arbitrary constant c. So this is a good place for us to draw the red line. So that is the solution for this question. Now the next question is we are expected to integrate integral x times ln x dx. Now by liet concept, let me just write that down here. We can see that the logarithmic function dominates. So we will have to start off by taking u to be ln x. So u is ln x and my dv is going to be the term which is present. That's going to be x times dx. So if I were to differentiate this, differential of u would give me du. Differentiation of ln x is 1 over x times dx. And integrating this would give me v is equal to x squared over 2. So this is the assignment part as well as the differentiation and the integration for u and for dv. So by formula we can substitute in the formula which I always used to mention. So I'm just using the right hand side, taking into account that you already know the left hand side. The left hand side is nothing but the question itself. So we got u times v. So my u is ln x and my v is x squared over 2. So place x squared over 2 in front of the ln x. Don't place it over here. Followed by a negative sign and integral sign and v du. So my v is x squared over 2 and my du is dx over x. So clearly I can cancel this x with this x, and that is going to be equal to x squared over 2 times ln x negative 1 over 2 times integral x times dx. So if I were to integrate that, we would get x squared over 2 times ln x negative 1 over 2 times integration of x dx would give me x squared over 2. I can rewrite this as x squared over 2 times ln x negative x squared over 4 positive arbitrary constant c. So that is a good place for us to draw the red line. So I have squeezed a question in this space here. I hope you don't mind. So we'll move on to the next question, students. So we got another question here, students. Integral x times cos 3x times dx. So we will use the principle of Liet by assigning the value for u. So u is equal to, you can clearly see this is algebraic and this is trigonometric. So algebraic comes before trigonometric. So u is equal to x and dv is equal to cos 3x dx. I differentiate this, I get dx, I integrate this, I get sin 3x. I have a coefficient of x to be as 3, so you divide that. Now this is going to be equal to uv negative integral v du. My u is x, my v is sin 3x over 3, followed by a negative sign. My v is sin 3x over 3. My du is dx. I can rewrite this as x times sin 3x over 3. I take the constant 1 over 3 out. That would give me integral of sin 3x dx. So this is equal to x times sin 3x over 3 negative 1 over 3. If you were to integrate this, this would produce negative cos 3x. Coefficient of x is 3, so I place it in the denominator. I rewrite this as x times sin 3x over 3 positive cos 3x over 3 into 3 is 9, and I add an arbitrary constant c. So this is a good place for us to draw the red line. Soon we will do the next question. We have to integrate integral ln x over x raised to the power of 5 times dx. Now this is, you might think this is algebraic, but this isn't an algebraic quantity because it is in the denominator. So we will start with the Liet concept, which we always used to mention. So from Liet I get u to be as ln x and dv is dx over x raised to the power of 5. Now differentiating this would give me du is equal to 1 over x times dx. Integrating this, I'm going to rewrite this as integral x raised to the power of negative 5 times dx. Upon integration, this is going to produce x raised to the power of negative 5 positive 1 over negative 5 positive 1, which is equal to x raised to the power of negative 4 over negative 4, which is 1 over x raised to the power of 4 with the 4 there carrying a negative sign. So this is my v. So when I substitute it in the formula, uv negative integral v du, this is going to be equal to, my u is ln x, my v is 1 over 4 times x raised to the power of 4 with a negative sign followed by a negative sign, and my v is 1 over 4 times x to the power of 4. There is a negative sign, so this will become positive, and my du is dx over x. So this is going to be negative 1 over 4 times x raised to the power of 4 times ln x, positive 1 over 4 times integral dx over x raised to the power of 5. and this is rewritten as negative 1 over 4 times x raised to the power of 4 ln x positive 1 over 4. I'm going to push this to the numerator, so this is going to become x raised to the power of negative 5 times dx. So this is what we would obtain, because I have already got that integral here. So this is going to be negative 1 over 4 times x raised to the power of 4 ln x positive 1 over 4. So integrating this would give me this. So that's exactly what I'm going to substitute there. So it's going to be negative 1 over 4 times x raised to the power of 4, which is equal to negative 1 over 4 times x raised to the power of 4 times ln x negative. This is 1 over 4 into 4 is 16, but I will write it as 4 squared times x raised to the power of 4. Now what we can do is we can either take x raised to the power of 4 out and write things as a common factor for the terms that we see here, or if you're happy with this, we can just add the arbitrary constant c and draw the red line. So that completes the solution for this question. Students, we are given this question: integral sine inverse of 3x times dx. So we are expected to use integration by parts. Now I will start off with the formula, Liet principle, Li, right? So this is an inverse function. So I will take u to be equal to sine inverse of 3x and my dv to be equal to dx. Differentiating this would give me du is equal to differential of sine inverse of x would produce 1 over root of 1 negative x squared. So this is going to be 1 over root of 1 negative 3x raised to the power of 2 times differential of 3x, that's going to be 3. Now integrating this will produce v to be equal to x. Now using the formula uv negative integral v du. So that's going to be equal to, my u is sine inverse of 3x, my v is x, so I'll substitute, or I should say I place the x on this side, followed by negative integral, my v is x, my du is 3 over root of 1 negative 3x raised to the power of 2, that's going to be 9x squared times dx. So this is what I've got. Now what I wish to do is I will use integration by substitution techniques. So let 1 negative 9x squared be equal to some t squared. I differentiate this, I get 18x times dx is equal to 2 times t dt. I will divide 18 by 2, that's going to be negative 9x dx is equal to t times dt. Now I can split this as 3x dx times negative 3 is equal to t dt. I'll push the negative 3 onto the right hand side, so it's going to be 3 times x dx is equal to t dt over 3 with a negative sign. Now you don't have to do all those things, you can directly substitute it with your own technique of calculation or manipulation. So this is equal to x times sine inverse of 3x negative. Now as I mentioned to you, this is 3x dx. So in place of 3x dx, I'm going to substitute negative t dt. There is a 3 there, so I'm going to place the 3 in the denominator. Root of 1 negative 9x squared, that's going to be t squared. So this is what I've got. Now I can rewrite this as x times sine inverse of 3x, negative negative positive, 1 over 3 I can take it out, so it's going to be integral t times dt, root of t squared will give me t. So clearly I can cancel these quantities, and that would give me x times sine inverse of 3x positive 1 over 3, integral of dt would give me t. My t squared is this, so my t is going to be root of the entire quantity, 1 negative 9x squared. So that's exactly what I'm going to write. So x times sine inverse of 3x, positive 1 over 3 times root of 1 negative 9x squared, positive arbitrary constant. See, and that is a good place for us to draw the red line for this particular question. Students, let me squeeze one more question here. We expected to integrate 2x times tan inverse of x times dx. So you can clearly see this is an inverse function, and inverse function comes before algebraic functions. So I'll start off with taking u to be equal to tan inverse of x and my dv to be equal to 2x times dx. Differential of u would give me du. Differentiation of tan inverse of x is going to be 1 over 1 positive x squared times dx. I'm going to integrate these two terms. Left hand side will produce v, the right hand side would give me 2 times x squared over 2. 2 gets cancelled, giving me x squared. So I will substitute it in the formula uv negative integral v du. That's going to give me, my u is tan inverse of x, my v is x squared, I'll place it here, followed by a negative sign, and my v is x squared, and my du is dx over 1 positive x squared. I'm going to rewrite this as x squared times tan inverse of x negative integral. Now in the numerator I got x squared, in the denominator I got 1 positive x squared. So what I would do is I would add a 1 and I will subtract a 1. So denominator remains as it is, so this has to be followed with the dx. So I'm going to rewrite this as x squared times tan inverse of x followed by a negative sign. I'm going to split this integral in this following fashion. So it's going to be integral of 1 positive x squared times dx over 1 positive x squared followed by a negative sign, integral dx over 1 positive x squared. Now clearly 1 positive x squared, 1 positive x squared can be cancelled. So this is equal to x squared times tan inverse of x negative integral of this quantity dx would give me x, integral of this quantity would give me tan inverse of x. So I remove the parenthesis and I can rewrite this as x squared times tan inverse of x. You got a positive tan inverse of x there, so I place that first, and then you got a negative x. Now you can take tan inverse of x out and write this as x squared positive 1 times tan inverse of x followed by a negative x followed by arbitrary constant c, and this is a good place for us to draw the red line. Students, I will state some special cases here. Now suppose you have e raised to the power of x and you have f of x, and that is followed by its differential. Then the final solution is going to be e raised to the power of x times the function. So this will be the solution. Say for example you have integral e raised to the power of x of ln x. Now the differentiation of ln x is 1 over x, and that is followed up in this fashion, and you are expected to integrate. Now directly you can simply state the outcome to be as e raised to the power of x times ln x positive c. So this is going to be your solution. Now we can see this in reality. Say for example, let me just show that to you. Now this is the question that is given, right? So I'm going to rewrite this as e raised to the power of x times ln x positive integral e raised to the power of x over x times dx. Now if we do not know this law, we will have to do this entire process. Now I got a I1 here and I got a I2 here. So let me just consider, let's consider I1. So what have we got in I1? I1 we've got e raised to the power of x times ln x times dx. Now if I were to apply Liet rule, my u is going to be my ln x and my dv is going to be e raised to the power of x times dx. differential of u would give me du. This is going to be 1 over x times dx, and integrating this would give me v is equal to e raised to the power of x. If I were to substitute this in the formula uv negative integral v du, this would give me u is ln x, my v is e raised to the power of x, negative my v is e raised to the power of x, my du is dx over x. So this is what I've got. Now I take this and I add it with, now adding I1 plus I2. So what have we got? This is my e raised to the power of x ln x, followed by negative e raised to the power of x times dx over x. But my I2, what is my I2? My I2 is positive e raised to the power of x times dx over x. So clearly you can see that these two can be cancelled. So hence you get e raised to the power of x times ln x, positive arbitrary constant c. Now this is a problem of lesser difficulty, so we were able to take in these many steps. But imagine you have a problem of greater intensity, of complexity. So in that case, this formula, or I would say this special case, comes in very much handy. So that is a very important point you will have to take into account, and we will see the next particular case. In this case, suppose you are given an integral of f of x positive x times f dash of x times dx. Then the outcome is going to be x times f of x positive c. So this is special case number 2, and let me have this as case number 1, and we will see a related question for this. Students, we are expected to solve this question, so what I would do is I would rewrite this question as e raised to the power of x times x, right, divided by 1 positive x raised to the power of 2. Of course, I've got the dx there. I will place the dx over here. Now what I wish to do is I would like to add a 1, and then I will subtract a 1, and then I'll place the dx here. So in this fashion I have not done any changes at all. So this is going to be integral e raised to the power of x. I'm going to open the parenthesis. This is going to be x positive 1 over 1 positive x raised to the power of 2, followed by a negative 1 and 1 over 1 positive x raised to the power of 2. So you got a dx there. Now clearly x positive 1 can be cancelled with the 1 in the denominator. So this is going to be integral e raised to the power of x of 1 over 1 positive x followed by a negative sign and 1 over. In fact, instead of placing a negative sign here, what I wish to do is I will place a positive sign here and place a negative sign here, divided by 1 positive x raised to the power of 2 times dx. Now if I were to take this as f of x, this is for your understanding, and that is 1 over 1 positive x. If I take the differentiation of this I would take u over v formula. So it's going to be 1 positive x times differential of 1, that's going to be 0, followed by a negative sign, and 1 time differentiation of 1 positive x is going to be 1 divided by 1 positive x raised to the power of 2. So this is equal to negative 1 over 1 positive x raised to the power of 2. So this is what I have got, right? You see that? This is f of x and this is f dash of x. So this is equivalent to the relationship that we have just studied. If we were to give a form of this fashion, integral e raised to the power of x of f of x positive f dash of x times dx, then the outcome is going to be e raised to the power of x times f of x with the arbitrary constant c. So this is equal to e raised to the power of x times my function 1 over 1 positive x. So I will place it in this fashion with the addition of the arbitrary constant c. So this technique which I just mentioned to you drastically reduces solving questions of this fashion. In fact, you have to understand that sometimes handling exponential quantities can be quite tedious, and this formula makes things simple. Since we are given this question, to handle this question we need to be a little bit cautious, because the general intention would be to add a 2 and subtract that 2 off, but that is not going to be working out in this case. So what we have to do is we'll have to start off with e raised to the power of x times x squared. Now instead of adding 2 and subtracting 2, what I would do is I would take away 4 and add 4. Now you will soon understand why I'm doing this. So this has to be divided by x positive 2 raised to the power of 2 with the differential operator dx. Now I would like to rewrite this as integral e raised to the power of x. I open the parenthesis. I start with x squared negative 4 as one term divided by x positive 2 raised to the power of 2. This is one particular term, right? So this is followed by positive, in fact I will place one more parenthesis, 4 over x positive 2 raised to the power of 2. So this is my second term followed by the differential operator. Now x squared negative 4 can be rewritten as x negative 2 times x positive 2. Of course you have this denominator x positive 2 raised to the power of 2 followed by 4 over x positive 2 raised to the power of 2 and the differential operator dx. Now clearly x positive 2 and x positive 2 can be cancelled, so that would give me integral e raised to the power of x of x negative 2 divided by x positive 2 followed by 4 over x positive 2 raised to the power of 2 and dx. Now the solution can easily be achieved if I can show that 4 over x positive 2 raised to the power of 2 is the differentiation of x negative 2 over x positive 2. So for that, let me just use this space here. So let me just take f of x to be equal to x negative 2 over x positive 2, and f dash of x I'm going to apply u over v method. So this is going to be x positive 2 times differential of x negative 2, that's going to be 1, followed by a negative sign x negative 2, and differentiation of x positive 2 is 1 divided by x positive 2 raised to the power of 2. So this is going to be equal to x positive 2 negative x positive 2 divided by x positive 2 raised to the power of 2. Negative x positive x can be cancelled, 2 and 2 can be added, giving me 4 over x positive 2 raised to the power of 2. So this is the quantity that shows that 4 over x positive 2 raised to the power of 2 is indeed the differential of the function x negative 2 over x positive 2. So since I have already achieved that, the result is going to be e raised to the power of x times x negative 2 over x positive 2. Of course we can place the parenthesis and of course the arbitrary constant c. So this is a good place for us to draw the red line. Students, I'll try to squeeze in one more question here. We expected to integrate sine of ln x positive cos of ln x times dx. Now this is a beautiful question. Of course the general temptation would be to approach this question by integration by substitution, but we don't have to do it like that, but we will take in the tools from substitution in an indirect fashion. So how do we do that? I'm going to start with taking ln x to be equal to t. This is to the base e, right? So I can clearly write x to be equal to e raised to the power of t. So if I were to differentiate this, I get dx is equal to e raised to the power of t times dt. So the original question can be rewritten as integral sine of, in place of ln x I'm going to substitute t, in place of ln x substitute t, in place of dx you're going to have e raised to the power of t times dt. So let me rewrite this in this fashion. So this is going to be integral e raised to the power of t of sine t positive cos t times dt. Now what is cos t? Cos t is nothing but the differentiation of sin t, isn't it? So if I were to take f of x is equal to sin x, and if I were to differentiate sin x, I would get cos x. So clearly this is going to be e raised to the power of t times sin t. But my t is nothing but e raised to the power of, this is ln x, right? So substitute ln x times sine of ln x, positive arbitrary constancy. See how beautiful this solution is. But the first glance of the question would literally stir up some apprehension. But since we know the technique, that apprehension would vanish in thin air and produce us the solution for this question. So we'll move on to the next question, students. I hope you are following all these questions that I've just shown you here, and I would suggest that you try these questions, and as I mentioned to you, practice is of key importance, and perfect practice is even more important. So having mentioned that, we will move on to the next question. Now, having got this result, I can get the same result using the case 2, which I have already mentioned. So now, just in case if you are wondering what is e raised to the power of ln x is, it's nothing but x times sine of ln x with the arbitrary constancy. So you can also rewrite it in this fashion. Now, as I mentioned to you, let me go to the special case which I've just mentioned here. Now, if I have a function along with x times the differential of that function, then the outcome is going to be x times f of x positive c. Now, we are given this question, right? Now, let me use this particular space here to show you what exactly we are trying to do. Now, this question can be rewritten as integral sine of ln x positive. I'm going to multiply x with cos of ln x, and I'm going to divide it by the same quantity. So this is what the problem looks. Now I'm trying to obtain this f of x positive x times f dash of x. Now if I were to take f of x to be as sine of ln x, then you can see that the f dash of x is going to be cos of ln x times differentiation of ln x. What is that? That's nothing but x. So clearly I can see f of x differential being present here along with x. You see that? This is nothing but f dash of x. So what is this exactly? This is nothing but integral of f of x positive x times f dash of x times dx. And what is this? This is nothing but x times f of x. But what is x? What is f of x? F of x is nothing but sine of ln x. So that is going to be x times sine of ln x positive arbitrary constancy. You see that? How we were able to achieve the same result. So these two results, they correspond. So students, will move on to the next question. Students, let's do this question. We are given integral of 2 times ln x positive ln x raised to the power of 2 times dx. So to do this question, what I wish to do is I would like to take ln x to be equal to t. From here I can write x to be equal to e raised to the power of t. Differentiating x, I would get dx is equal to e raised to the power of t times dt. So this can be rewritten as integral 2 times t positive. In place of ln x I substitute t, that has to be raised to the power of 2. In place of dx I would substitute e raised to the power of t times dt. I can rewrite this as integral of t squared positive 2 times t times e raised to the power of t times dt. Now we know this formula. What is that? Integral e raised to the power of x of f of x positive f dash of x times dx is equal to e raised to the power of x times f of x positive c. Now based on this formula, we got f of x to be equal to t squared, f dash of x to be equal to 2t, and that is exactly what we have here, right? So the function and its differential are present, and that would mean the solution is going to be e raised to the power of t times t squared. But what is my t? My t is nothing but ln x, and that has to be substituted here. So that's going to be ln x raised to the power of 2 positive c. Now of course e and ln, you can rewrite it as x times ln x raised to the power of 2 positive c, and that is a good place for us to draw the line. And this is a beautiful solution and as well as a beautiful question. Now students, the same question can be done with the second variation. So this is the variation which we studied, and I'm going to apply the variation which I've just shown you a little bit earlier. So I'm going to rewrite this question. We have got 2 times ln x positive ln x raised to the power of 2 times dx. This is what we have got. I'm going to rewrite this in this fashion. So I'm going to state it as ln x raised to the power of 2 followed by 2 times ln x times dx. Now what I wish to do is I would like to place x here and divide it by x. So in this fashion, what I'm trying to do is I'm trying to achieve f of x positive x times f dash of x times dx. This is exactly what my requirement is. So my target is this expression. I should have it here. So if I have this to be my f of x, the question is, if I were to differentiate this, there's going to be 2 times of ln x times differential of ln x will give me x. So clearly you can see f of x added with x times of f dash of x is exactly what is present here. So clearly I can rewrite that, or this entire quantity, to be as, so this is nothing but x times f of x positive c, right? That is the case that we looked into. Hence, using this, the solution can now be rooted to as x times, this is my f of x, that's going to be ln x raised to the power of 2 positive arbitrary constancy. So this is a good place for us to draw the line, red line, and we can see that the solutions agree. The only difference between the former and the later is that we do not bring in the exponent here in case of the variation 2. We just handle it with the given function itself. So depending upon what is your preference, you can do that. Now I'm going to teach you a quick technique for handling integration of this form x raised to the power of n times f of x dx. Now usually if the degree of n is greater than 1, then you will have to apply integration by parts multiple times. Suppose they are given you 3, then to solve this question you will have to consecutively apply integration by parts technique. So that is quite tedious. So this method which I'm going to show you will simplify everything. Now we are given integral x squared times cos 2x times dx. Now what we have to do is, this method is usually called as the DI method. So we will have to use differentiation and integration. So what we will do is we will divide it in 2 columns like this. We will have a d here and we will have a I here. We will take the components given here based on our u. So in this case we got algebraic and trigonometric. So if we had to apply Lie, x squared will be the first term which will fall under the differentiation category, and cos 2x will fall under the integration category. Now differentiate x squared. Differential x squared will give me 2x, and then differentiation of 2x will give me 2, and differential of 2 will give me 0. That's fine. Now you integrate cos 2x. Integration of cos 2x would give me sin 2x divided by the coefficient of x. In this case, the coefficient of x is 2, so we will have to place the 2, and the integration of this quantity should be followed. So that's going to be cos 2x divided by the coefficient of x, which is 2, so that will make it as 4, but the sign has to be negative. That's fine. So next is integrating this quantity. Integral of cos 2x would give me sin 2x. The coefficient of x is 2, so that's going to be 8, but the sign will be retained as it is. So this is the table that we have got. Now with regard to the sign component, what we will do is we will start off with a positive sign here, followed by a negative sign and a positive sign and a negative sign, alternating. And then what we will do is we will club the first term with the second term like this, followed by the second term with this term, and then this third term with this term. Of course, we don't have any term for 0, so we can just drop that. So if I were to rewrite this, the solution is going to be x squared times sin 2x divided by 2, so you can place that 2 there, negative times negative, that's positive, and there is a 2x there, place that 2x times cos 2x divided by 4, and a positive times negative, that's going to be negative, so sin 2x divided by 8, positive arbitrary constant c, and it's a good place for us to draw the red line. So this is the solution. So imagine applying integration by parts this many times. It is not going to be easy, but this technique will simplify the entire process. Students, I want to squeeze in one more question here. We are expected to integrate integral x raised to the power of 3 times e raised to the power of 2x times dx. So this is of the form integral x raised to the power of n times f of x times dx, and we can apply the method that is shown here. So we start off with d and I, we design the column, we take the first term x cubed followed by e raised to the power of 2x, we differentiate x cubed, we get 3 times x squared, we differentiate 3x squared, we get 6 times x, we differentiate 6x, we get 6, we differentiate 6, we get 0. So now we integrate e raised to the power of 2x, that's going to be e raised to the power of 2x divided by 2. We integrate this is going to be e raised to the power of 2x divided by 4. We integrate this is going to be e raised to the power of 2x divided by 8. We integrate this is going to be e raised to the power of 2x divided by 16. So now what we will do is we will place the sign. So we start off with positive, negative, positive, negative and positive, and then we will start the mapping. X cubed goes with this term, 3x squared goes with this term, 6x goes with this term, 6 goes with this term. So if I were to write them down, this is going to be equal to 3x squared times e raised to the power of, I should start with x cubed. So this is equal to x cubed times e raised to the power of 2x over 2, and then I have a negative sign, so 3x squared times e raised to the power of 2x over 4, then I have a positive sign, 6x times e raised to the power of 2x over 8, then I have a negative sign, 6 times e raised to the power of 2x over 16, with the arbitrary constant, and that is a good place for us to draw the red line. Now students, you can apply the same DI technique even to this question. So we actually can do this question by integration by parts using UE technique, but we can also use DI method. So if we were to take x to be as d and I to be as cos x, I differentiate x, I get 1, I differentiate 1, I get 0, I integrate cos x, I get sin x, and then I integrate sin x, I get negative cos x. So the signs would be positive, negative and positive. The mapping would be, I would start with x going to sin x, -1 going to negative cos x. So the solution for this is going to be x times sin x, negative times negative is positive, 1 times cos x will give me cos x, positive arbitrary constancy. So this is what we have got. Now I can show you by UV technique. See, if we were to use Liate, and we know the formula, integral u dv is equal to uv negative integral v du, and I take my u to be as x and my dv to be as cos x dx. I were to differentiate this, I get dx. I integrate this, I get sin x. Applying this in the formula would give me x times sin x negative integral sin x times dx. So this is going to be x times sin x. Integral of sin x is going to be negative cos x. This is equal to x times sin x positive cos x, positive arbitrary constancy. So clearly you can see this is exactly what we have achieved with this DI technique. Let us do another question. Probably you can pause the video and try this question by the technique which I've just shown you and check the answer. So we expected to integrate x times cos 4x. So I'll draw the tabular column, a table. So it's going to be d and I. My d is going to be x, my I is going to be cos 4x. I differentiate x, I get 1. I differentiate 1, I get 0. I integrate cos 4x, I get sin 4x divided by 4. I integrate sin 4x, I get cos 4x divided by 16 with a negative sign. So I place the signs here, start with positive, negative, positive. Then I perform the mapping, x goes with this term, negative 1 will go with this term. So this is equal to x times sin 4x divided by 4, negative, negative, positive. So this is going to be cos 4x over 16 plus arbitrary constant c, and this is a good place for us to draw the red line. So if your solution is same as this, then you can give a tap on your shoulder and you can move on to do the next question. Now we are going to get into questions of a special nature involving exponential functions as well as trigonometric functions. So suppose you are expected to integrate a quantity like this. So what I would do is I will start with my table d and I. So I will take my d to be as cos x and my I to be as e raised to the power of x. Now it is imperative to understand that this differentiation cos x is not going to be terminating at all. In other words, I would be alternating between cos and sin. And this integration is also not going to be terminating at all. So what are we to do to achieve the solution? Simple. Catch the pattern which is recurring. In other words, you have to look for the pattern that is repeating itself. So having mentioned that, let me start off with differential of cos x. That's going to be negative sin x. Now differential of sin x is going to give me cos x. Of course there is a negative sign there, so place it. Now let me integrate e raised to the power of x. I get e raised to the power of x. Again I get e raised to the power of x. Now you can clearly see I started with cos x and e raised to the power of x. I am having here cos x and e raised to the power of x. So the pattern has already occurred here. Now let's place the signs. So this is going to be positive, this is going to be negative, this is going to be positive. Now when we are writing the terms, let me just show you how to write the terms. So the solution for this is going to be, so the mapping starts here, cos x with e raised to the power of x, that's fine, and then negative sin x with e raised to the power of x, that's fine. Now the third one, once you have the recurring here, you will have to take this term along with this term. That's exactly what you have to do, right? So I'm going to show you how to write the solution. So the first quantity is going to be e raised to the power of x times cos x. That's fine. And this is positive. The second quantity has got a negative sign preceding it along with this negative. So that would make it positive. And it's going to be e raised to the power of x times sin x. And the third term, you got a positive times negative. There is one particular thing I need to do here. Now what I want to do is, I will just start off with taking let I be equal to this term. So I will simply write it as I, because it is eventually this quantity, right? E raised to the power of x times cos x with a negative sign. So let me just place the value I there. Now we are started with let I be equal to this quantity, and this quantity has been integrated. Because of the recursion that we see here, this has been placed as I with the sign. Of course, on the left hand side I have got a I there. Now what I will do is I will push this I to the left side. That would make I positive. I is equal to e raised to the power of x times cos x positive e raised to the power of x times sin x. Now this is going to be 2 times I is equal to e raised to the power of x times cos x positive e raised to the power of x times sin x. I can take e raised to the power of x out. This is going to be cos x positive sin x. I got a 2i there. I can push the I down. I can push 2 down. So that would give me I is equal to e raised to the power of x over 2 of cos x positive sin x, positive arbitrary constancy. So that is the solution for this question. In fact, what is my I? My I is nothing but integral e raised to the power of x times cos x times dx. So this is a good place for us to draw the red line. Students, let us do one more question to reinforce this concept. So we are asked to integrate e raised to the power of 2x times cos x dx. So what I will do is I will start off by taking let I be equal to integral e raised to the power of 2x times cos x times dx. So I will draw my table, the d and the I. So my d is going to be cos x and my I is going to be e raised to the power of 2x. So I differentiate this, I get negative sin x. I integrate this, I get e raised to the power of 2x over 2. And then I differentiate sin x, I get cos x, the sign is retained. I integrate this, is going to be e raised to the power of 2x divided by 4. Now clearly we can observe that we started with cos x and e raised to the power of 2x, and that is exactly what we see here, cos x with e raised to the power of 2x. Of course there is a constant 4 there, but we can handle that constant. Now let us just place the signs. So this is positive, negative, positive, and then we will have to map it. So the mapping is completed. Since there is a recursion, we reverted in this fashion. So if we were to write it down, we will have to write it in this manner. So this is equal to cos x, it's a positive sign, cos x into e raised to the power of 2x over 2. So this is going to be e raised to the power of 2x over 2 times cos x, negative, negative, positive, and then you have e raised to the power of 2x over 4 times sin x. Now I need to multiply e raised to the power of 2x over 4 with cos x. The only issue that we have got is this 4. So I would place a negative sign followed by that 1 over 4 times I. So I will push this to the left. So it's going to be I positive 1 over 4 times I is equal to e raised to the power of 2x over 2 times cos x positive e raised to the power of 2x over 4 times sin x. Taking the LCM, this is going to give me 5i over 4 is equal to e raised to the power of 2x. It can be taken out common. In fact, 2 can also be taken out common. So this is going to give me cos x positive sin x. Of course, there is a constant there, so it's going to be 1 over 2 being present here. I need only I. So cross multiply. If I were to cross multiply, 4 will go over there. 2 can divide 4. It's going to be 2 times e raised to the power of 2x. 5 can come down. So this is going to be cos x positive 1 over 2 times sin x, and with the arbitrary constant c, and on the left side we got I. So this is a good place for us to draw the red line. Students, we are given this question: integral 1 positive x negative 1 over x times e raised to the power x positive 1 over x times dx. So what I would do is, foremost I will split the terms as 1 and x negative 1 over x, and then I will use the distribution of e raised to the power x positive 1 over x. So that is going to be e raised to the power of x positive 1 over x followed by a positive sign, and x negative 1 over x times e raised to the power of x positive 1 over x times dx. Now over here I'm going to take x out. So this is going to be e raised to the power of x positive 1 over x positive. If I were to take x out, this would become 1 followed by negative 1 over x squared times e raised to the power of x positive 1 over x times dx. Now this is similar to our case integral f of x positive x times f dash of x times dx, which produces the result as x times f of x positive c. Now if we can show that this quantity as a differential of this quantity, then the solution is straightforward. So let me just take f of x to be equal to e raised to the power of x positive 1 over x, and I need to find f dash of x. The differential of this is going to be e raised to the power of x positive 1 over x times differentiation of x positive 1 over x. This is nothing but e raised to the power of x positive 1 over x. Differential of x would give me 1. Differentiation of 1 over x would give me negative 1 over x squared. So clearly you can see this is exactly what we are seeing here. You see that? This is exactly what we are seeing here. So this would mean, you can just draw a line there. So this would mean the solution for this, the solution that we have to get here is going to be x times f of x. So in this case my f of x is nothing but e raised to the power of x positive 1 over x positive arbitrary constant c. So that is a good place for us to draw the red line. So this is a lovely question. I hope you understood the concepts that were being used in this question. So as I always mention, students, practice makes perfect, or to be more reinforcing, I should say perfect practice makes or provides perfection. So with this we will complete this particular lecture. The fourth lecture is completed and we have studied quite a bit in this, and we will meet in the next class. Thank you students, have a wonderful day.